Hi, first I should introduce myself. I'm Stephan Clemenc. I'm professor in applied mathematics at Telecom ParisTech. I'm the head of a rather big research team fully dedicated to machine learning. Maybe you have heard my colleague Florence Dalchet earlier this afternoon. I'm also the holder of an industrial chair with various companies, Valeo, PSA, BNP, Safran, Morpho, Criteo. In this chair, we are not producing machine learning technologies, but machine learning algorithm concepts and analysis. Sometimes it's very useful to address complex problems, such as the problem of weak signals. I'll try to explain how extreme value theory comes into play in this kind of problems. Truth should be said, current machine learning algorithms, they involve very simple statistics, essentially sample mean statistics, residual sum squares, the count of number of errors in a classification rule. And this work is essentially motivated by predictive maintenance, the health monitoring of very complex infrastructures, such as an aircraft. And the main problem I'm going to cover is the problem of anomaly detection and how to reduce the number of false alarms. And I'll try to give a statistical learning overview of performance criteria and algorithm, and how extreme value theory somehow permits to increase performances. So what is nice with big data is that rare becomes observable. The vast majority of machine learning techniques, they focus on analyzing the center of the mass of the data set. Here, we are particularly interested in the tail behavior. Complex infrastructures are monitored by dozens, hundreds or thousands of variables. We are living in the era of Internet of Things. And the problem with the main issue with anomaly detection is that it's mainly an unsupervised problem. We have no labels on the data. Essentially, we have the concept of rarity should replace the labeling. The main assumption in this approach is that here we assume that anomalies correspond to extreme observations. This is not necessarily true, and not in all systems, but here it's our assumption. But of course, the reverse is not true in general. And in particular, if you assume that there is a one-to-one correspondence between extremes and anomalies, the number of false positives can be drastically. So, what is anomaly detection? A very simple definition is it's an observation that is very far from the center of the mass of the data set. It's very simple in the univariate case. It's either much higher or much smaller than a central statistic, such as the median or the mean. But in a dimension larger than 2, it's complex. But you see that around an anomaly, there should be very few over observations. Most techniques, just like in the supervised setting, they consist in learning the normal behavior, just building a critical region, and when your observation lies outside this region, then you set the alarm. Of course, it's much easier when you have supervision, when you have labels, when you have indicator of variables indicating whether the observation is abnormal or not. Even if it's weakly supervised, techniques should use this kind of information, but in most situations, you are fully unsupervised, and the problems are becoming much more complex. But in the supervised setting, we have many techniques. Of course, anomalies are rare, so it's the probability of observing an anomaly is very small, so it's very unbalanced, at least in the training stage. But the theory and the algorithm are very well documented. All they rely on the principle of empirical risk minimization. You want to minimize some criterion, typically in pattern recognition, the misclassification error. What algorithms do, they are replacing this unknown risk by the statistical version of it, and they minimize a smooth or convex version of this loss. The theory is very well documented. Typically, you have a rate, universal rate of order square root of n, when n denotes the number of training data to feed your learning algorithm. So this is well-known folklore in machine learning. Here, in anomaly detection, we want to build some region in the feature space, and where the vast majority of the observation should lie. Typically, you expect that 95 or 99% of your data should lie in this region. Of course, there are many regions that contain 95% of the data. You want that which minimize some criterion. Typically, you want the smallest region, in some sense, that includes the vast majority of your data. So small means it has a small volume, and you need some reference measure. So the basic approach to anomaly detection in machine learning is the minimum volume set approach. You want to minimize the volume of your region under the constraint that it contains at least alpha% of your data. Of course, if alpha is small, you are recovering the modes of a distribution. And when alpha is small, by taking the complementary, you recover the tail behavior of your data sets. Okay? Of course, the theoretical solution is just a sub-level set of the density of your data. But here in machine learning, we face the curse of dimensionality phenomenon. We do not want to estimate. It's completely irrelevant to try to estimate the density of the observations. We focus on a decision rule in machine learning, and typically algorithms, they consist in replacing the unknown distribution by the empirical version. This is the well-known empirical risk minimization paradigm. Of course, you include some tolerance level because you're replacing the theoretical distribution by the empirical distribution, and you try to solve this problem. You have guarantees, and now you have many algorithms available that try to solve a smooth version of this problem. But sometimes you want more, just than having a system which indicates an alarm or not. You want to rank all the observation by degree of abnormality, from the most normal observation to the most abnormal observation. You want some scoring function, and you can evaluate it by more complex criterion. You can plot the mass of your critical region obtained by thresholding your scoring function against the volume. So it's like if you are familiar with rock curves, it looks like the symmetry of a rock curve. But here you expect a curve that increases very slowly in the beginning and very fast near to 1. So you have criteria for this unsupervised problem, which is good in practice. So I come back to extreme value theory. So as I said, our main assumption is that anomalies correspond to extreme observations. What is extreme in a multivariate setting, it remains to be defined. And the main idea of the mathematical technology I'm trying to describe is that we want to discriminate between normal behavior among extremes and abnormal behavior. This way, we may expect to reduce, crucially, the false alarm rate, which is very expensive in practice. That's our task, to distinguish between large anomalies and normal extremes. So our claim is that anomalies among extremes correspond to those which direction are unusual. You have several ways of representing multivariate data. Here, you can take the norm of your observation x plus the angle, just the polar coordinates. Okay? And what is nice with multivariate extreme value theory, it gives you a framework to analyze the dependent structure among the extremes. Okay, this is completely described by an object which is called the angular measure. Here, in the bivariate case, this is the simplest multivariate case. The first thing is to, of course, you want an algorithm that is independent from the choice of the units. So you need somehow to standardize all the components of the vector x. Typically, you apply a rank transformation. You standardize all the components so that they have the same distribution, uniform or Pareto distribution. And you analyze the directions in which extreme value occurs. And the idea is to define a region in the extreme part of a feature space where normal extremal observation should lie. And if it's not the case, then you raise the alarm. This framework holds because actually there exists a very large class of multivariate distributions called regularization distributions, such that asymptotically you can tensorize the distribution as a tensor product between a Pareto distribution for the modulus for the amplitude of the vector x and certain distribution on the set of possible values for the angle on the unit sphere, which is called the angular measure or the spectral measure. And we can analyze this spectral measure. It completely encodes the dependent structure among the extremes. Again, this is a very simple plot. If there is independence between the components, you have data gathered along the axis. If not, if there is a certain dependence, then in the middle of the space, you have data that are aggregated. But this is a very general non-parametric framework because all possible dependent structures can exist. And the idea is to apply this minimum volume set algorithm to the angles that you are forming using this standardization. So the algorithm are generic and very simple. You can reuse all the algorithm listed before, but you apply this to the transformed data, to the angles formed by the training data. So of course there is an assumption. There should exist a reference measure on the sphere, on the set of possible angle values. And sometimes this is not fulfilled because it may happen that, of course, you have independence. So you have no preferential directions. So this technology is also coupled with dimensionality reduction techniques, but in the extremes. Of course, maybe you're familiar with principal component analysis. Essentially, they try to analyze and to look for possible dimensionality reduction around the mean. But here, this should be the same thing, but for the extreme observations. Actually, the goal of the algorithm we have introduced is to automatically determine the groups of components that can be simultaneously extremes, while the others are small. Okay? Sometimes you have an anomaly in an aircraft because a collection of variables that are monitoring the system are simultaneously very large. That's why you and may lead to a catastrophe. So the idea is that in practice, the support of the angular measure, it doesn't weight every facet of the unit sphere. And it's to recover the facets of the unit spheres that are typically weighted by the data. So we have introduced, it can be summarized by this simple sentence: it cannot run everywhere at the same time. So in general, you have a few groups of variables, and with few variables in these groups that are explaining the extremal behavior. So the answer of the analysis and the algorithm is that, sure, we can recover these groups of variables with theoretical guarantees. And in practice, when we analyze real data, we see that this sparsity assumption, that there are few groups, compared to the number of possible groups, if you have d variables, of course, you have 2 to the power g minus 1 possible subgroups. So rapidly, the combinatorial effect can be very annoying. But this plot shows that, yes, in real data sets, you have this sparsity, and you can expect to reduce drastically the dimensionality and to apply the anomaly detection techniques in the extremes to these subgroups of variables. And so I skip the technical details. This way, you can really improve traditional anomaly detection techniques. So we have produced a variety of experimental studies showing that it works in practice, and also it can be combined with visualization techniques. When we are trying to recover the sparse support of the angular measure, it may remain an uncertainty about the facet to which an observation belongs to. So we have introduced a mixture model. Maybe you are familiar with k-means, for instance. It's sort of k-means, but in the extremes. And it permits to assign to any observation probability that this extreme, this anomaly, correspond to a certain subgroup of variables. And this way, we are able to define similarity measures between anomalies. For instance, this is a plot describing a flight of a certain company. And this way you can visualize the clusters you may obtain, or is an anomaly similar to another one, or is there an anomaly which resembles none of the anomalies already observed. This is a tool that can be directly used with no knowledge of machine learning. But essentially it is based on these extreme value statistics and on the approach I have previously developed. Of course, this approach can be applied to other problems. Classification in extreme regions, for instance, it may be relevant in various applications, in finance, for instance. You can decompose the basic criterion, such as the misclassification error this way. But due to the rarity of extreme observations, sometimes your classifier is not efficient in these regions. We can introduce another notion of risk. Typically, the classification risk above a certain threshold level. We can define an asymptotic framework showing that this classification risk converges to an asymptotic risk, and derive quite simple algorithm which consists in training pattern recognition algorithm, classification algorithm, to the angular data. But those corresponding to observations that are beyond a certain level. And again, this really increases the performance of the algorithm in the extreme regions, any kind of algorithm. That's all. These results, these algorithms are documented in various papers presented in the major conference devoted to machine learning. And some of the algorithms are available on our GitHub, are completely open source. That's it.
Thank you very much, Stephan.